I'd like to welcome up Mr. Michael Sutton. Very honored to have you here today.
Am I on? Yeah, okay. So yeah, I wanted to say it's a special day because Ireland has proven to be on the solar system. Yeah, so my name is Michael Sutton. Contribute to Kaspa's research and development. I enjoy both worlds. I'll get to that. So I'll focus about the scalability of Kaspa and how it's translated from theory to practice. That's the main subject of my talk. And I'll also touch about our system principles, how we think about what we want to solve, and our some kind of guideline we have in the way we try to design and solve problems and ask questions. And I'll end with the goal of being the ultimate sequencer, like a bare metal system layer which serves as a sequencer for anything above it. So that's like an interesting view of that. I think Shai has much more experience than me in speaking. I think it's the first time I've been out of Israel speaking about Kaspa. I've gave a few research talks in the past, but never about Kaspa, and never in English yet, so be patient with me. Yeah, so I wanted to say I'm 21 years old, plus 15, for those who wonder. Yeah, so like Shai explained, and like we all know, or some of us know, GhostDAG decouples scalability from security. You can be scalable. So that's a new world. And I'm not going to talk about that yet. I mean, I'm not focusing on that, but that's my starting point. We have a world where the protocol no longer limits the ability of the system to scale. So what does that mean? You have to press like twice, but strong. Does that mean we can infinitely scale to any BPS or TPS? So the answer is obviously no. You can't infinitely scale because, why? Because we have another value. It's called decentralization. So we don't want a participant in the peer-to-peer network to have to buy the most expensive hardware in the world. We want to keep it affordable. We want it to be able to run on commodity hardware. So that's a constraint of the system, that we have a given budget or we look at typical systems and we want them to be able to run Kaspa. And then you still want to scale. So how do you scale given some resources? So scaling up to the hardware limits is what I call HPC. It's not exactly the traditional. Usually when you say high-performance computing, it means like a world of supercomputers and all that. But I'm referring to the aspect of high-performance coding approaches, parallelism to the maximum possible, like actually using a classic system of computer with 8 cores, 16 cores, and utilizing it to full capacity. So you get this world where everything you optimize either helps throughput. You either increase the TPS of the system because you optimized, or you lower the barrier to the cost of the hardware. So you have a new zone, which is, okay, I'll give a background before I dive into that. So the way I see, as a computer scientist, I look at cryptocurrencies. The way I see them up until now, up to Kaspa, it's an intersection of 3 different research domains. Now, the first one is cryptography. Cryptography is not like cryptocurrency or something like that. It's the world of basic utilities and primitives that allow secure operation, like PKI is a public key infrastructure. When you have a wallet and you sign a transaction, so only if you sign, only if you had the private key and you signed the transaction, it can be verified by anyone else that you're the owner of the funds, and it's unrelated to the consensus system you use with the DLT. It's a cryptographic primitive, a result of a lot of research, which helps us create PKIs. So cryptography is also, you can see it also in mining. Like proof of work is based on the fact that no one can guess what nonce or what number would bring you the target block. You have to solve the puzzle, and it's based on hash functions being irreversible. And that's a very classic, basic cryptography primitive that all of proof of work is built on that concept. So cryptography, people can be experts in cryptography. It's a completely different, completely full, huge research domain. And cryptocurrencies use cryptography extensively. But they also need consensus, which is another research domain of having a distributed system and being able to reach agreement, to have settlement, to agree even though you're a decentralized network and there's no central authority. The fact that you can agree on something, on a state, is another research domain called distributed systems research. And proof of work consensus is actually just a new child in this domain. It's been going on for decades. Yeah, so I like to give the example of, I'm sure most of you might not need this example, but I'll go for it anyway. What's the need for consensus? So it's called the double spend problem. So say you have a bank account and you have like 1,000 euros in it, and there's no you cannot be in minus. So you have exactly that amount, and you can only use that. And you and your wife go to two different things where you pull money, ATMs, and two different cities, and you both click the 1,000. You want to pull 1,000, and you both click the final button at the same second. What happens? So one of you gets it, the other will get an error. What happened? It doesn't depend exactly on the order. It can be the second one who clicked. It depends on the request that got first to this central database somewhere, and a mutex in the code that got that request first and captured this amount and gave it to one of the requests, and the other one will fail. Inherently, it uses the fact that there's a central point that makes decisions. Because the system doesn't care if you or your wife get the 1,000. It just cares that not both of you get it, and that it's consistent. If you wouldn't be pulling like from the ATM, if you would be sending to someone else, and your wife would be sending to a third person, and you did the same thing, so the system doesn't care where it goes, because you're the user, you're trying to mix it up. But it wants to be consistent. It wants to know it went to someone, and that's what defines the state of money. So that's what we want to achieve in consensus without this centralized point. We want to know that there's a distributed network, and the network, different parts of the network might be seeing the first operation first or the second one out of order, and you still want the system to converge on one financial state. And that's a challenge. It's kind of a magic, I think, when you think about it. Being able to have this fast network, especially at making the decision of convergence in a matter of seconds, like Kaspa does, is like kind of the thing you're like, okay, how does this happen? How does it make sure that it's not confused? How do they all know they agree? What guarantees that? And that's why it takes like a security proof in a paper to actually prove that no attack strategy can manipulate this decision. And no matter what, anything unthinkable, it doesn't matter. The proof has to cover all possible options of an attacker. That's why it's not so easy to prove consensus and protocols. It might be a good opportunity to mention that Shai mentioned DAG Knight, so I'm a co-author of DAG Knight. And I'll say a little more about that, even though it's not like it's not the topic of this talk. The third element is Shai touched on this, algorithmic game theory, what we call mechanism design, like designing systems in a way that each rational player would do what's best for him. But if you design the system properly, they all act for the benefit of all. If you design the system in the right way, so you want it to operate well when each actor is acting in its own good. Because people are rational, you want them to make the right decision. So the mining system is one primary example of such a dynamic. You give, the money supply goes to the miners. So the rational strategy is to mine fairly and do the right thing. And the benefit for everyone is the security the system gets from the collective mining effort. So this is all over. And like, in a way, for us in Kaspa, we're now mostly at the first stage, the third stage of research for when we're thinking about the future problems like MEV, oracles, fee markets, stuff like that. That's where most of the research will go. But I'm here to focus on the fourth dimension that I mentioned, high performance. So my personal perspective is that I met Jonathan also at the Hebrew University at 2018, maybe 2017, but I only joined a year later, more or less. And I was doing my master's in HPC, high performance computing. I didn't touch like consensus research at that point. So I also had vast industry experience in programming and leading groups. And I was doing HPC research, like running complex irregular problems and hardware with multiple GPUs. How do you manage that hardware beast, for instance? And I was everything I touched was graph algorithms based. So the DAG is a type of a graph. So that's another connecting point. But I feel like Kaspa now is like in this unique place, intersection point between of high performance, system engineering, system research, and being able to give value to a real world currency like Kaspa and allow it to scale more and more. And yeah, this scaling would also only benefit as hardware gets cheaper. We're not at the limits. I mean, it's an evolving, hardware gets cheaper and gets more capable. So that's also something to note. It's not only about optimization, it's also a natural evolution of the hardware world. So here enters Kaspa on Rust, also known as Rusty Kaspa, like the mature Kaspa. That's why I came up with the name, RK. So RK was an initiative started like by myself 2 years and 2 months ago. Like first lines of code, no code base based on it, completely new code base. First lines of code in it were written at July 22. And it was an effort to rewrite, optimize, and fully redesign Kaspa's peer-to-peer node to the extent that it can run 10 BPS and more. So the idea was to redesign it. The original node that was ran by Kaspa when Kaspa mainnet launched was written in a different language and with a different kind of architecture, which was monolithic. Single operation, and every moment in time it does one thing mainly in terms of the consensus layers. There was a lot of activity in the communication layers, but the core consensus engine, what we call, used to do like one operation at a time. Because it's complicated to do things in parallel. You can't, especially when you need consensus. You're like running code that all nodes in the network need to run and get to the same result. So naturally you do it like carefully and one at a time. And if you add parallelism into this because you want to have tight performance, it's not so easy to do it in a way that this property of consensus code Like when you speak about systems like Kaspa and their code base, there's the sacred part of the code, which is consensus code. Like if one condition is somehow depending on the order of events arriving at the node, and would make some node makes this decision and the other node make another decision, the network would split, literally. Every line of code in that area, and thousands of lines, is like taken much seriously. And this effort was about parallelizing that part, like doing everything possible concurrently and parallel, using multiple threads, using various memory optimizations, database optimizations, everything we could to get to where we are now. So concurrency, highly optimize the consensus engine with like a processing pipeline. Think about a restaurant where you have a pipeline of things. One person is washing, another is doing that, and you're doing different tasks at the same time. So that's what we call a concurrency pipeline. And then at each station, we also have parallelism, multiple workers doing this job. I'll touch more on this. Another thing turned out to be very challenging when we first launched 10 BPS was the real-time relay, the broadcasting of 10 blocks per second. Yeah, now I see it. 10 blocks per second. It was the first, like, 1 BPS is still very close to the amount of time it takes to propagate a block. So you have 1 block per second, and it takes about a second to propagate. So the system is more or less, there's no need to tightly manage all aspects. But when you go 10 BPS, usually the propagation time is more like 500 milliseconds, 1 second. So you're producing more blocks in this period of time. And that, making this structure converge all the time and being tightly connected, that like what is required from GhostDAG to be secure, takes a lot of analyzing and tightening this interaction and making it like perfect. The feeling I had at the time is that it's kind of art to do this part of the code. I don't know why. Rust was also used to redesign the way clients communicate with the node, like to redesign the solution of wallets, exchanges. There's many customers to a node that are not the node itself. We call that RPC layers, remote procedure calls. And there was a big effort on redesigning that part so it can be very flexible and adapt to web clients and any kind of client, and we can easily extend it on the node level. So it was so the rewrite was not only about performance, but it was also about doing it right in all aspects. And above that, led by Anton, he's also known as Aspect. He was leading. He is leading a huge effort above this RPC system and creating a SDK and a software development kit, which is what external developers can now use without needing to know exactly all the details of complicated core logic. They can rely on a library that is maintained by the best knowledge people have in Kaspa. So that's a huge part of Rust, the Rust project in Kaspa. And maybe I didn't write this down, but possibly the main benefit of rewriting a system is that you get new developers joining you and creating the system again. So more and more developers joined us. Not talking about 5 in a month. I'm talking about 1 good developer every 2 months showing up. And you need to push yourself in. We don't make it easy, but that's part of the test. And he just pops up and is very interested by the technology. And he's been around maybe, watching, quiet. And then he just starts contributing. And the fact that he was helping to build now a new component is now a win forever, because he's now involved in this. He knows this in his blood. He actually designed it now. And as this is the scaling of the development task force is like beyond important. It's like you have no idea. Yeah. So like I mentioned, timeline started 2 years ago. It's the currently deployed Kaspa's mainnet software. 97% of mining hash rate goes through a Rust node now. I think around 60% of the peer-to-peer network is already Rust nodes. Maybe more. I don't know. There's no complete knowledge about the peer-to-peer network by design. And testnet 11, we call it testnet 11 to differentiate it from classic testnet, which runs 1 BPS like mainnet. So it backed by Rust nodes, has been running since January this year. Like I said, over 222 million blocks, already passing mainnet, which is running for 3 years almost, with 90 million blocks, because it's running at a pace of 10x faster, so it took only a few months to catch up. And most of the time it has like, we don't always push it to peak performance. Most of the time it has like at least 100 blocks, transactions a block on average. So that's like 22 billion transactions in the last 9 months. So the start was humble. We started with mostly the core original contributors. Ori Newman, which is in the crowd, was my biggest assistant in starting this. Elichai Turkel, which is a brilliant applied cryptographer and a Rust enthusiast, gave a big boost on starting. He implemented like a lot of the crypto signatures, hashing, all that aspect in Rust pretty fast, and was like one less major thing to think about. That was a huge boost. And Anton, which I mentioned before, was also a big Rust fan. And he helped like forming the structure and to begin with, and advise, and just his wisdom and experience. And then you see this graph shows like the activity of the code contributions in the node software through the last 2 years. It has its peaks. And if you look at this is like activity of the last month. So 25 merged pull requests. Pull request is like a code contribution, like a chunk of noticeable piece of work by someone. That's like 25 of that. 17 offers. It started small, but it's already scaling. And it's like I said, it's very important. The testnet 11, here's a video of it, of 10 blocks per second. When I took this video, it had each block is a real-time like point, and it actually included 300 transactions, all validated in real time. And it forms this very nice DAG structure. So like blocks, I was running in parallel to Shai. We weren't communicating exactly what we're going to talk about, but there are collisions. There is a fraction of collisions.
We'll sort it out first.
No, I know what to say. So I kind of want to share what our guiding principles are, how we think about problems, why we choose as a community or as a group of people this way or another. So Kaspa was designed with the BTC ethos in mind, being like a thin verification and settlement layer for peer-to-peer action, transactions, money, and so forth. What we don't want to be a computational layer. We want to keep L1 nodes running commodity hardware. We don't want to have 3,000 transactions, which each can be a complicated smart contract operation that needs to be run and creates state and a whole bunch of activity. But maybe we can still use the advance of technology to kind of gain the best of all worlds. So modern technologies actually allow us to be fast. When I say fast, like Shai said, it's blocks per second. It's what we call the frequency of the system. Like how fast does it respond? Like Jonathan once said, we want our internet money to be fast. We want to ping it and to be ponged. We don't want to wait for 10 minutes. We want it to work, to be instant. And by the way, that like also known in UX worlds, 100 milliseconds, 10 BPS, which means average block time is 100 milliseconds, and known to be the fastest response a human can recognize. Like below that, there's not so much of benefit in that area. There's benefit in other areas. So using the GhostDAG line of research, GhostDAG is a paper you can read like the first 2 pages, and you get it. It's intuitive. It clicks, almost like when you read Bitcoin's paper, original, which also like is like an aura feeling sometimes. But it's a fruit of a line of research, and some of the ideas which produced it originally, like Ghost, which is different than GhostDAG, are not really so secure. They can increase throughput, but they have a liveness problem and stuff like that. So it was a thought process that you can see in the line of research Jonathan put out through the years from 2012, I think, to 2018, with a group of researchers in the Hebrew University. And GhostDAG is just the end of that, not the final stop. DAGNITE is another stop after that, which achieved something GhostDAG didn't. But GhostDAG allows us to be fast and to be wide, to have throughput. We can scale, and with that, we don't compromise security. But we still want to be thin, meaning like not fat. We don't want to do these complicated computational things. So zero-knowledge technology wasn't even mature enough 6 years ago when we were thinking about Kaspa. We were looking at other solutions which have some compromise. But since in the last few years, zero-knowledge technology is amazingly showing us that you can verify and not compute. It's a known, one of the most well-known open problems in computer science is what we call NP equal P. If you know a problem given a solution can be verified in short time, like in tractable time, meaning a computer can do it in a few minutes, does it mean that the solution can be found in short time as well? So it's an open question, but it's widely believed that the answer is a resounding no. You can verify a solution. We have multiple problems we don't know how to solve efficiently, meaning you need exponential time to find a solution, and exponential times becomes intractable pretty fast. And we know how to verify the solution indeed works. Common, well-known problems are like finding the travel agent problem, finding a route in a graph that goes through all cities without repeating anything, stuff like that. So what I want to emphasize is that zero knowledge is like an interesting example of the fact that you can verify something. Almost certainly, I think it has this small probability, but unrealistic. So you can verify it without computing. So that's like very untrivial, and it exactly fits the way of Kaspa being a fast settlement layer for sequencing events, ordering them, and reaching agreement on how they're ordered, and then interpreting them can be done by a layer above, and still be proven to the base layer, and have consequences on the base layer, because the L2s can prove that they followed the order L1 dictated, and they did the computation correctly, and that means now that this Kaspa can be sent to this, that, and there. So this dual relationship, pegging and unpegging and stuff like that, comes from the fact you can prove with zero knowledge proofs, like a large computation with a very small proof. And we're planning, our design goal is to implement a constant system where the smart contract layers above Kaspa will constantly provide proofs to L1. That's like a current design effort I'm also part of. So like I mentioned, and like here's where we kind of intersect a little bit. Kaspa's goal is to become the ultimate sequencer in a sense. You want a fast system with thousands of transactions per second, converging on the order, very fast. How fast, by the way? So that's where DAGNITE adds. So each line of this slide is like a big research problem in a sense. Do you need to depend on some a priori knowledge about the system delay or not? So GhostDAG would answer, yes, you depend. The rate of convergence, how fast this order of events is settled and not going to change anymore. So that depends on the a priori assumed delay of the system, while that in DAGNITE it will not. So that's why people interpret this as like DAGNITE scales to internet latency, which is kind of a way to put it, but then it sounds like you increase throughput, which is not necessarily the case. It means that the responsiveness in the system scales to internet latency. And as internet latency reduces, the system can converge, and you can, as a user, that means you can improve your transaction. You can be certain about the transaction you've just sent faster. So that's being an ultimate sequencer. It's part of this vision of being an ultimate sequencer. I think of it as like TCP to the internet, in a sense. It's a backbone, bare metal like protocol for sequencing events very fast. Not all applications need this. Not all applications need a global ordering. I think part of this effort and part of this day is, for me, is to get a better understanding on what applications, what's the attributes of an application that needs this kind of service. That's like the question we should starting to get answers for. Another attribute of sequencing is not only about security. You don't only want that the order of events would be finalized so that you can't double spend, for instance. You also want it to be fair. And that's where MEV resistance comes in. And that's why we think that even though smart contracts where the MEV activity will go on are actually at the layer above, by dictating the order by L1, without understanding the meaning of a transaction, L1 will not understand what this transaction exactly means. It's only going to get the proof of what it did. But it can still help by the distributed, the decentralized force of miners. And if we design the system properly, speaking of mechanism design, we can make a system where the ordering is fair in terms of miner extractable value. That's where we're going to have. And this comes, surprisingly, I find this fascinating because high BPS, we think about it as a frequency, as fast, and throughput, it gives you throughput. If you fix the amount of transactions the block gives you, you increase the block rate so you get more throughput, faster response, and all that. But it's not only an enabler for things, it also creates a new surface, because things like the fee market, Shai described, that the rational strategy of a miner is to apply randomness to his transaction selection. Why? Because he has no idea what miners next to him are doing. And there's a parallel block next to him doing the same thing. And if he would choose transactions deterministically, so we would all choose the top 200 paying transactions, and would all be choosing the same. And the system obviously can't pay the fee to everyone. Only one of them counts. So this random order, eventually converging, would dictate, so you kind of flip a coin and you may lose if there's 10 blocks per second. So chances are that if you use a deterministic strategy, all miners would do the same, and you only have 1 of a 10 of a chance to winning these transactions. So that's why it's rational to use probability. And it comes from the informational gap of high BPS. High BPS means we don't know what happens next to us, and that changes the way we behave. Even if blocks propagating throughout the world at speed of light, if you have 30 BPS, you're guaranteed to have parallel blocks, because traveling throughout the world still takes around 50 milliseconds. So even if we take it to the extreme, it's still, there's no zero latency. So there are parallel blocks, and then there is informational gap. And this informational gap is good for a fee market. It's also good for creating auctions, because you cannot have an auction if you know exactly what the previous block was bidding on. Okay, it's unfair. You have an advantage of knowledge. The fact that you don't know what others are doing is critical for creating a good auction system and for repaying back things like MEV value. Another example, so it's not like it somehow happened that high BPS creates a new surface in terms of fairness and the possibilities of design space. Another example is oracles, which it's a known problem of how do you provide external data on chain. You have a smart contract that depends on the state of some out in the world variable that is influenced by real world events or users engaging it. And then you need some trusted setup sometimes to report the state of this, the price of this token. The smart contract depends on that. By using this high BPS and creating like voting systems where all miners of a round of 10 blocks vote, and you run logic in a way that if a miner deviated from the collective outcome, it gets penalized. So you incentivize correct reporting, and you can create a system where you can actually become an oracle, a trusted oracle for external sources, actually, like through this mechanism on chain. So that being the ultimate sequencer, that's my talk. I hope you enjoyed.